आ रहा है? आ रहा है ना? Yeah, good evening. Good evening. Okay. So today I'm going to take about AUC ROC curves. I not told you about the AUC ROC curves, na? I'm fine now. Yeah, good evening. Good evening. Okay. Fine. Got it. Okay. So let's talk about AUC ROC curves. What are those curves here? I'm nice now. Okay. I'm fine. Far better from the cold now. I took a lot of care. Yeah. Okay, so good evening. Okay, so let's go ahead with AUC ROC curves. Okay, AUC ROC curves means area under the curve What does it mean? Basically, AUC ROC curves are those curves. The AUC ROC curves represents the graphical representation of confusion matrix, right? It represents graphical representation of confusion matrix. Like we are having a confusion matrix as one of the parameter for the matrix, just to measure the model performance. In another way, if we want to see the performance in graphical mode, so there is a AUC ROC curves are there. That is a graphical representation here. Okay. So how this AUC ROC curves are created? Basically, what happens when we talk about, yeah, hello. Wait, hello. Okay, AUC ROC curves. See, what happens basically now? Generally what happens, whenever we have any data related with classification, binary classifications. So for the binary classification, the partition between the two categories takes place with the help of a threshold value, that is a 0.5. This is a default threshold value through where it is measuring whether any provided data output moves towards the higher side, towards the 1 side, or towards the 0 side here. This one is the threshold value. Okay. So what happens when this is the threshold value? So we would be having some, I say, confusion matrix based on the data which is moving towards the data which is moving towards the 0 side. Means if I say I'm having the data for the diabetic patients, so some of the patients are suffering from diabetes, some of the patients are not suffering from the diabetes. So those data are being segregated with the help of threshold value. That one is a 0.5 default here. Second, if we lower down this value, suppose this 0.5 is lower down. Let's say I'm lowering down this value. Instead of 0.5, we are lowering down this value here. So here I'm changing this now. See, in AUC now, if I'm taking this case, suppose the threshold values I'm taking as a 1. And here one needs to segregate the values, whether the data which we are having, those data are having diabetic patient or non-diabetic patient. So if the threshold values come to 0.1, so what happened? All the data below 2.1, they are indicating that these persons are suffering with no diabetes. What does it mean? 0.1 means we can consider 10%. So in this case, what happens that if I say generally that if I'm having 100 patient data, so 100 patient data, if we gave to segregate the data accordingly to the diabetic or non-diabetic performance. So here, the model will check it out, 0.1 as a threshold value. And here, all the values which are below 0.1, they are going to be considered as a no diabetic people. So it means 10% of the people are considered as a no diabetic people. So the remaining people, the remaining 90%, if I say the remaining 90%, these all fall into the diabetic case. It means 90% of the people are diabetic if the threshold value goes to 0.1. Rest are, these are 0. So this would be the kind of confusion matrix will be there if 100 number of patients are there, 100 number of records are there. If I change this threshold value, suppose this threshold value, I'm changing it here. Suppose this one I'm changing. So this 0.2 is there. So what will happen? All the data which is below 2.2, which is below 2.2, all the data which is below 2.2, I say this data, this zone. This zone says that the patient is a non-diabetic people. The patients who are coming below 2.2 threshold, they are non-diabetes people. They do not suffer with any diabetes. And the above left out 80% people here, the above left out 80% people, they are suffering with diabetes. So it means in this case, when threshold value goes to 0.2 automatically, so here, my confusion matrix will be, I say 20% of the people are suffering from the diabetes, 80% of the people are, 20% of the people are okay, 80% of the people are suffering from diabetes. This would be the new confusion matrix based on to new threshold value. If I change this record a little bit more, suppose I say, I'm changing this record here. So if I take this record, suppose I say 0.9. 0.9 is the threshold value. So it means all the below people, below 0.9 value, all the people below to 0.9 value, all the people below to 0.9 value, they are non-diabetic people. So they are non-diabetic people. It means 90% of the people are non-diabetic. The remaining one above means these are the 10% people. They are suffering from the diabetes. So here, these people are suffering from the diabetes. So these confusion matrix will keep on changing as per the values of the threshold will keep on changing. So when these values will change, so correspondingly, there are other formulas also work, such as recall, precision, okay, recall, precision, or specificity. So These formulas also work just by taking the values from this confusion matrix. And these values also keep on changing as per the values are changing internally. Okay. So by taking those values of what? Recall and specificity. So here, just wait. By taking the values of recall and specificity, we can make, by taking the different values of recall and specificity, we can make the AUC ROC curves. So how we can get these values? We are having functions present inside models. With the help of them, we can get these values. Okay. So if I talk about the AUC ROC curves, what are they? With the help of confusion matrix, various threshold values we receive. From there, when we get the different sensitivity and specificity value, with the values of sensitivity and specificity, we can draw this curve. This curve shows the area. The more the area is covered, so that shows that how much the accuracies are moving upside. So it means 0 and 1, 0 and 1. So here, if my curve goes in this way, so I will say maximum area under the curve is covered here. Maximum area under the curve is covered here. Okay. Right. So in this case, we can say like, if our curve goes in this way, so I'll say like 0.8. It means I say like 80% of the confusion maximum means 80% of the model performance is coming up. It means I'll say nearby accuracy is going up to 80%. If my curves go little below side, if say suppose my curves go here, so it means the area covered is less. So you can see the black lines. So here the area covered is less. So this one is the AUC ROC. So it means area under the curve is less. So it means my accuracy is 0.7. 0.7 is 70%. If the AUC ROC curves are drawing here, up to here, so it means the area covered is less here. Area is less here, na? You can see here. So AUC ROC is less here. So I can say here nearby 0.5. So it means 50% of the 50% nearby accuracy is there. 50 or 60, you can say it here. So here, you can see here, AUC ROC curves here. This one is the AUC ROC curves. AUC ROC curves are basically graphical representations of confusion matrix. So this is also one of the important evaluation matrix. AUC ROC curve is also one of the most evaluation matrix for any classification model performance here. So here you can see this one here we are having sensitivity. Sensitivity itself is a recall and 1 minus a specificity. Here we are having. So you can see here ROC. AUC itself means area under the curve. So here ROC means receiver operating characteristics, means AUC area under the curve, ROC receiver operating characteristics. Receiver operating characteristics curve tell us about how good the model can distinguish between two things. Okay. Better models can accurately distinguish between the two. So here we will be having a function, predict probe function. With it, we can get the values of sensitivity and specificity, which will be helping us to draw the AUC ROC curves here. So basically, this one is, it is showing you that it is just showing you the distinction between here. Confusion matrix, it is going to show you, but it is not exact confusion matrix here. It is just showing you that we are having two classification data, and here, see this one. Here it is showing you that we are having two classification data. One is any of the data which we are having, one shows the positive classification or the negative classification, and here are certain errors present. Okay, so instead of that, just I'll show you here. You can see the formulas here. Just wait here. Recall is true positive over true positive plus false negative. Okay. And this one is a specificity. This one is a specificity. Already you're aware. That one is a true negative value over true negative plus false positive. Okay. So we need to consider these two values. One is recall, which is a sensitivity, and another one is a specificity, which take this formula. So actually, when we take this sensitivity and specificity, so the curve is going this way, but just to make the data in this way, here it is taking sensitivity and 1 minus specificity just to make the data in this way. And this one is basically AUC ROC curve. This one is a AUC ROC curves, which shows if maximum data are covered, maximum graph is covering the area, that shows well the model is doing there. So AUC ROC curve is the area under the ROC curve. This score gives us a good idea of how well the model performance is working. See now this one. From here you'll be getting idea. Suppose here I say you are having some data for the classification, binary classifications. So here, if I want to plot a AUC ROC curves here, so your model is working very well. So if your model is working 90% correct. So here you will be having AUC in this way. You can see this one, this particular graph. So you will be having the AUC in this way. So it means you can see this one, you are having a sharp rise here. Okay. If in case my area is less, this is 90% it is showing. If my area is less, suppose my accuracy is coming down, means that one is 80% nearby, 0.8. So you can see here, my area will be this much. You can see here the tiltness is coming here. Here in 0.9, you can see the coverage is there, area is covered here. So from here, your area starts covering here. But in 80%, no, your area starts from here. Here in 90 it is working here, in 80 it is working here. And if your model is having 70%, you can see the gap here. There is nothing area covered now. From here, your area is covered. That shows what? That shows what? That shows that your area is less covered. Okay. And suppose this one you can see. This one. Okay. So this shows that the area covered is 0.5. 0.5 means 50% area is covered. So you can see the differences into the areas covered here. Here, less area covered. Here, 70% area covered. Above 80% area, 90 here. Got the point here? And in case, suppose you are getting 1. So in that case, this would be the sharp one. This would be the sharp one because that is touching this one. So from here it is, the area is covered. More the area is covered, more accuracy is there. So that shows you AUC ROC curves. So basically AUC ROC curves shows you that how well your model is performing. Okay. So these all formulas are working. We call this, we call here this we call sensitivity, which is a recall. We can call it a true positive rate also. And 1 minus specificity is also known as a false positive rate. It means here, because when this is drawn here, so this one is a sensitivity, this one is 1 minus specificity. Okay, then your graph is drawn. So basically, this can be termed as true positive rate, and this can be termed as false positive rate, FPR and TPR. Okay. Here. So here, this is a matrix only, just a matrix. So matrix means at the end of your model, means you are taking your data set, you are doing all things, but when you come to the end of the model, when you are checking out the matrix, so there your AUC ROC curves come. So here I'm taking a earlier file. These are the earlier file. These are the earlier file which already we had created. A lot of file we had created now. I'm using the same files. No new files here. So the same file you can open and you can click on cell, run all you can do. And then add some more code only at the end. This is the file I had opened. Which one? Cancer file I had opened. You can open any of the binary files, cancer file even you can open. Already this file is based on the binary evaluation that whether the patient has the person is suffering from the cancer or not. Here I had used a logistic regression. Okay, so what happens now? This logistic regression, this LG. So basically this model, this LG, there is a predict probe function. There's a predict probe function inside the logistic regression. This will help us to find out the various values of the TPR, false positive rate, and different threshold values. Okay. So this LG, we are going to take this instance. I'm going to take this LG. Already everything is done. This one is already done now. Already matrix are done. Normal matrix are done. Accuracy, confusion, classifications are done. Okay. We need to add a small code here at the end because this is one of the evaluation matrix which shows you the graphical representation here. So here I had added the code you can see here. From sklearn, import ROC curves. So I had just called it from sklearn.matrix, import ROC curve. Okay, everything is predefined. I need to call it here. Okay, from sklearn.matrix, import ROC AUC score. Okay, so curve I need because with this curve, I will be feeding few values and that will be plotting the curve. Now for the curve, we need some values. For the values here, I'm just calling logistic regression predict probe function. So I'm taking a LG.predict probability. Predict probability is one of the function which will start creating certain probability. So here we are passing the test data, and here it is taking all the rows and started predicting one. So here it is predicting, just start predicting the probability of the provided data or the provided test data, whether the patients are suffering from diabetes or not. So here it is just giving me some data. So here basically it is just giving all these data, whatever data are coming here. These are the probabilities only. It is showing you some probabilities. So what we'll do, this probability which we are taking from predict probability function here, here. This predict probability function. Why predict probability function? This predict probability function, so I'm going to take it here. And here I'm passing that one in ROC curve. Because to make the plot, I need value of false positive rate, true positive rate. These two values I needed. So here I'm sending ROC curve. Inside the ROC curve, I'm sending the actual values and the predicted probability. Why predicted probability, which are calculated value, which are the calculated predicted values here. I'm sending it here so that this ROC curve will give me false positive rate and true positive rate, which we will be using for the creating ROC curves. So here it is returning back. Here it is returning back. What? It is returning me three things. ROC curves is returning me false positive rate, true positive rate, and certain threshold values. So here certain FPR, TPR, and some threshold values it is giving back to me. Now here we will be using this FPR and TPR. These FPR, false positive rate, and true positive rate. So come here. So here I'm going to use these FPR and TPR value. These FPR and TPR value, I'm going to use it here. Here. So here I'm using matplotlib. This one PLT is a matplotlib.plt instance is there, dot plot method here. So here I'm just making 0 to 1 and 0 to 1. I'm passing these two arrays here. 0 to 1 means here from 0 to 1, just start plotting. 0 to 1, start plotting. Okay, now it needs this K minus minus is nothing. This it will start making these dots. Okay, dotted lines. Okay, now here now I need the value, this FPR and TPR. You can see carefully here. I am passing inside the PLT dot plot here false positive rate and true positive rate. Okay, false positive rate and true positive rate. And label whatever label you want to put. Logistic regression. Now here I'm putting false positive rate in X label and Y label true positive rate. Title as the logistic regression PLT.show. So here it is showing you the evaluation matrix here. So here it is showing you AUC, ROC curves. So you can see here, some distortion is there. So when it is showing now, it means it is not exact one. Some distortion is there. It means some below 1. It is below 1. So let's say, let's check it out is score here. From here, so there is one of the method you can see here. ROC AUC score. Here I am passing test Y, LG.predict test X. Here I am passing the true value and predicted test X data I am passing, means actual value and predict value that I am passing so that we can get AUC score. So here it is having 0.94. 0.94 means here it is saying 94%. 94% means here 94% your score is there. 94% your score is there. 94% your, I say, accuracy is there. So that's why this one, there's some distortion is coming here now. So this one is the AUC ROC curve. Okay, so this much your data are covered with a logistic regression. So what it is saying, with logistic 94% accuracy is there with logistic regression. Okay, now the same data, so this is okay. Now what I did, I took decision tree classifier. This is the next classifier I took. Okay, so with next classifier, I created the instance because we can use a decision tree classifier here because decision tree classifier is here it is going to check it out whether the patient is suffering from the cancer or not. So here we can use the decision tree classifier. DT I had created, dt.fit predict accuracy, we are checking it. So this dt.predict prob function we can use to take out the values of false positive rate, true positive rate. We can use these values to make the AUC, ROC curves. So here you can see, I had used this dt.predict probability function. Here I'm taking test X data, just take all the rows and start predicting the probability of 1. Here dt I'm using decision tree. So here I'm taking you can see predict probability function will return this y predict probability, predicted probabilities. So I will pass on this predicted probability into the AUC ROC curves here. So I'm passing inside the ROC curves true values, actual true values, and the predicted probabilities. Done. This is going to return false positive rate, true positive rate, and the various threshold values. These two values, false positive rate and true positive rate, that I'm going to use it here inside the plt.plot function. Rest I'm going to use this plt plot just for 0101 means start plotting it in this way. This is 1, this is 1, this is 1. Okay, and here I took FPR and TPR just to plot it here. So with these values, in this way, it will start plotting it here. Rest is labeling is there, X label and Y label and title is there. If I want to check it out, the score, ROC AUC score, here, test Y, dt.predict test X, AUC score here. This is there. So here, test Y. So here test Y, dt.predict test X. So here it is showing, we can pass on the actual value and the predicted value. So in this way, decision tree score classifier is coming. So here you can see it is little bit 94. See how it is coming. This one is the area covered. AUC, ROC score here. Okay, so 0.94, your score is there, right? If we are having a 90% as a score, that is much better. If we are having a 70%, that is less. So highest the score is, better it is. Here, if I'm getting score here, see, my area covered is too high. So this is good. So it means logistic regression is performing well. Here, area under the curve is high. So it means my logistic regression is working perfectly. LG is making how much score? Also, when we are checked it out, it is creating a 0.94. So it is okay. And what about this one? Here also it is just showing decision tree classifier. It is showing you this one. It is showing decision tree classifier is also showing you 94. So it means both are showing nearby 94, 94. Both are okay. At the same time, if I say any third model you are having, any, suppose I say GNB. For GNB also you can make it same process you are having. But for this, I'm getting in this way. So it means area under the curve is less. So here I'll say like 0.65 it is making. So it means here 65% your model is working well. So it means if I say Dysentery is on 94. LG is on 94, GNP is on 65. So two are working better, GNP is not good. So in this way, we can conclude it. Yeah, shall I proceed now? Okay, so this one is a AUC, ROC curves. Okay, now let's see here. There's a concept of pipeline basically. Pipeline means to do the entire work into pipes. Generally, when we work with machine learning, we do our work with a control flow. Control flow means here, in a very simplistic way, if I say, suppose I say you are doing some task and you are making a flow. Suppose you're checking out for certain whether your data is null or not. You are doing certain simple imputer operation if it is null. You are applying a standard scalar. Then you are using a model. Then you are using a cross validation. Means so many process you are taking step by step, step by step, step by step. In this way, you are taking it here. Okay. So if we want to organize some process into the pipe, okay, right now we are doing all the processes independently. Independently, we are going to do it here. But if we want to do the entire process in a pipe, this pipe, this pipe, this pipe, pipe. So here what I can do, I can make a pipeline. Okay. So there is a concept of pipeline in ML. So basically means this is just a conceptual understanding I'm giving to you so that you should know. Okay, you apply or won't apply, that is your choice here. So basically, inside a pipeline, suppose I want to make a pipe, general pipe. So what I can do here, I can give here, suppose that I want to make a pipe that before sending a data to the model, just to first make a standard scale data and then apply any ML model. Suppose I'm saying this is a tree classifier, you apply it. Fine. So here we can create a pipeline. Here we can give certain name to this pipeline that before sending any data directly to the model, just to make the standard scalar or flow it with a dysentery classifier. In a simple way, I'm telling you. So here we can make a pipeline, and then this pipeline could be flown through what? This pipeline could be having the input and output data. For an example, I'm taking you a very simple example here. Suppose here, okay, see this data. Here you can see, I just create a pipeline that standardizes the data, then creates a model here. Okay, here I just call certain library, cross-well score, standard scale, pipeline. Okay, from sklearn.pipeline, import pipeline. I just call this pipeline here. This is available inside the scikit-learn and any model I had created here. Okay, I just called it. Fine, I'm loading any data currently. Any data, I just loaded PMA Indian diabetes, I had loaded it here. Okay, so with I'm just loading this directly URL. My data will be loaded here, and I'm making the segregation of input and the output directly. Okay, so here, if I want to make a pipeline, let's see how to create a pipeline, basic pipeline here. But it is again optional as a conceptual understanding, I'm telling you. So here you can see, I'm creating a pipeline. Here I'm creating a pipeline. Estimators is a blank list. Here I'm creating. Estimator is a blank list. Now I want to fill this list here. Currently it is a blank list here. I want to append this list with standard scalar. So I want to fill this list with a task, standard scalar, and another append is decision tree. Done. So here, this is an estimator. Done. Now here, I pass this particular list of work. Suppose do the standard scalar, then decision tree. Fine. I pass this list here inside the pipeline. So this pipeline is coming from where? From sklearn.pipeline, import pipeline. This pipeline I'm going to call it here. So this pipeline is going to make the pipe of standard scalar and DTC. So here inside the pipeline, I had just given the estimator. So inside this estimator, we are having a pipe of standard scalar and decision tree. So here, this one is an instance of pipeline we had created. Now this one is passed here inside the cross-well score. So when the model start working here, so it will be cross-well scored. Before cross-well score, what it will do? It will be taking the entire data. Oh, here it is taking all the data, input and output, making the data standard scaled. Okay. Using the decision tree classifier and then making it cross-validated, and then finally it is going to take it. So basically, pipeline is for making the pipe work. Okay, pipe work. The same task we are earlier also doing, but we are doing those tasks separately. Individually, I'm doing it here. Individually. Right? So this is one of the concept, but it is generally means it is one of the concept here. You should know that, right? But here you can take an individual task also. Let's go to gradient descent. Let's understand what is this now. Till now, like we came to one thing. See, you had learned about linear regression. You came to know about that how the model works. So model starts predicting the data based onto the equation. And in this equation, there is term known as error. This error is reduced. This error should be reduced. So this is a mean squared error, which shows you that your error should be reduced. Okay, right? Your actual data minus your predicted data, right? making the square of it, divided by n. So mean squared error means basically you already know that if your error comes down, your results are up, your y is up. So overall the point is here that whenever your model is learning any data, the terms come with the error, and this error is basically, which is a mean square error, should be reduced. If it is reduced, your y will be automatically up. Got the point here? Got the point here? So this should be there. This should be there, remember. But actually, how this error should be reduced? So various algorithm uses various techniques so that here this error should be reduced. So we call this error as the loss function also. Okay, so we call this error as a loss function also, or certain time technically we call it a cost function also. I can call it a cost function or loss function. Basically, why cost function or loss function? Because the more we are having it now, that is not good. It should be reduced. If it is reduced, this should be up. Y should be up at any cost. So basically, now what happens? There is a term basically. There are certain algorithm which works to reduce down this error. That is known as a gradient descent. So this is one of the algorithm. Till now, like you had worked so many algorithms. Now you had worked on linear regression, I say. You had worked on linear regression, you can say, lasso, ridge, KNN, logistic, GNB, MNB, SVM, and many other. So the point is here, this is one of the algorithm, gradient descent algorithm. So basically, you can see it here. How does gradient descent work? This one is a normal equation which we are having. This one is a cost function. Cost function itself means mean squared error. The goal of the mean squared error is here we are having a mean squared error. This one is the y prediction. This mean squared error, this one is the function of the mean squared error. This mean squared error, we can call it a cost function. Cost function is a function that measures the performance of a model of any given data. So cost function quantifies the error between predicted values and the expected values and present in the form of single real number. So this one is a MST cost function, mean squared error cost function. This is having the same form now. Now here we try to minimize the cost function here. So we are having goal to reduce the cost function. So here we need to minimize the error rate here. Okay. So if we want to minimize the error, there is one more algorithm which will try to adjust its internal parameter to come down for the errors. So there is one of the algorithm, gradient descent. Now let's see how this gradient descent works. So again, there is a, just wait. There's again high mathematical terms associated, but I'll just explain you very simple term here. How it works. Suppose for a very simple example here I'm taking. Think out. This is a hill. This is a top of hill. You think it out. This one is a top of hill. Here, one person is standing. I tied up I tied the eyes of the person. Okay, I tied the eye of the person so that the person cannot see. Now, what I say, we are on the top of the hill, top. I tied the eyes of the person, or we can say means the person cannot see. Simple way I want to make the person cannot see. This one is a lake here. This is a lake. This is a lake. Now, this person wants to no, he is thirsty. This person cannot see. This is the situation I gave, and this person is thirsty. He needs water. Now he has to think that there is a water here. So it means he has to search the water. Now where the person will move, because this is the only place to walk now. So he has to search for the water. Of course, when the person will come down, some water will be there. He has an idea. So this person, just to eliminate the thirst, he started approaching this hill. Now let me take some steps. He start taking, because he cannot see. This is a situation. So he start taking this situation. See. Very small. When he will reach, he will take a lot of time to reach this water. To this point, he will take a lot of time. So this is very curious. Maybe just due to the thirst, the person can elapse. He means maybe he do not have any more strength. So because the steps are very small. Okay, this is first case I'm telling you. The person is taking very small, so that he cannot fall. So that he's taking very small, but I feel he is unable to reach. Unable to reach means he will take a lot of time. This is not an optimized way. Now, let's take a second case. This person now, he start taking a big step. Big step. 1, 2, 3, and 4. And he dipped inside the water. This is also not correct. He is inside the water. We said that this person needs to drink only, not to dip. So the point is that what would be the optimized step? I'm giving a term. Optimize. Optimize means what would be the optimized way through which this person can reach to the target and drink the water. That's all. So the optimized way is here the person can take optimized steps. The person can take optimized steps. You know, optimized steps means neither small, not very big. Just like here, he's here inside the lake. No, because he is a thirsty only, no? So he reached. So this is the optimized. I say this is the optimized. This is the optimized way. So optimize a step. So here what happened? The person is taking optimized steps or optimized rate it is taking so that he can reach to the corner, and he took the water, and now he's no more thirsty. So this is the target. Got the point? So the term comes optimized. Optimized means the person should take that many steps that is required to reach at the corner and into effective time, not very low time, less time, or not very fast time. So the point is, this is not the story of a person. This is the story of the error. Consider your errors are here. errors are here. Suppose any model we gave, errors are here because initially errors are there. So what gradient will do? I'm talking about the gradient. What gradient will do? Gradient descent algorithm will internally start tuning its parameter. It is having certain parameter as a learning rate. It will start tuning the parameters inside it and start taking the optimized values. It start taking the optimized values to reduce down the errors, It is taking this gradient descent is starting taking reduce down the errors, and here it is reaching to the corner only. Okay, so that is there. So remember, this is a gradient descent. If I say in gradient descent, what happens? Gradient descent algorithm is there. My errors are here. So in gradient descent, errors are try to minimize. Error tries to minimize by the gradient by adjusting the parameter learning rate, optimized learning rate, so that here it could reach to the optimized value. Optimized value is the least error value. Means here, if the errors are high, so it will try to reduce down the least error value by taking optimize steps. So it will internally tune the learning rate parameter internally with different value internally, so that it can reduce down the error. Okay, it can reach to minimum. It can reach to minimum value. So here you can see gradient descent is an iterative. Iterative means come down, come down, come down, come down, come down. Iterative process. Iterative. It goes on moving this way so that the errors could be down. So gradient descent is an iterative optimization algorithm for finding the local minimum of a function. Okay, and it is a mathematics working behind it. Gradient descent is simply used to find the values of a function parameter coefficients that minimize the cost function as far as possible here. So cost function means error should be reduced down at any cost here. Gradient descent is an optimization algorithm used to minimize some function by iteratively moving in the direction of steepest descent as defined by the negative of the gradient. In machine learning, we use gradient descent to update the parameter of our model. Parameter refers to the coefficient in linear regressions and Bayes neural networks, basically. So this one here, it is just reducing down the errors. If our errors are here, so that one is reduced down here, up to here. Okay, so these comes just with the values of various adjusted parameter internally. So here, these all are adjusted with its learning rate parameters and other parameters. So there is a this is stochastic. There is a gradient descent algorithm. So here, when we talk about the gradient descent algorithm here, we are having SDD regressor and SDD classifier. So SDD regressor means stochastic gradient descent. Stochastic gradient descent regressor we are having. Just like we work with the other regressor, so here we are having this one more algorithm as the regressor here. So here you can see, I just given here, see here, I just call here, I just importing various libraries, and I'm calling one of the data set, any data set one you can call it here. I'm calling the standard scalar also, Crosswell, and certain pipeline I'm going to call it here, certain more metrics I'm going to call it here. Here you can see, I'm just loading here, Boston data set here. Inside the data frame, I'm loading input data. Okay, I'm taking the feature names, and here into the Y, I'm just calling the output data. Now here I'm going to use this HGT regressor. I'm just going to call, I already called this one here from sklearn.linear model HGT regressor. This one is a stochastic gradient descent regressor, which will be internally working for what? Internally working to reduce down the error at the maximum level. So here I'm going to call it. So here I'm just creating a pipeline. Pipe is the blank list I had created. Pipe.append. It means just to apply the standard scalar, apply the PCA. It means if I say in load Boston 13 columns are there, just reduce down to 8 columns here. Then apply stochastic gradient descent regressor. These are certain predefined parameters, right? Taking the same parameter, certain alpha learning rate, maximum iteration penalty. These are certain predefined learning data there. This one is the gradient, which will try to reduce down the error to the lowest values. So learning rate is optimal. This one is the iterative method, will continue till the errors are least here. Once the pipeline is created with the stochastic gradient descent regressor, this pipe is created. This pipe is going to be settled down inside the pipeline. So here I just call pipeline here. So sklearn.pipeline, import pipeline, inside the pipeline I pass the pipe. Here I just create the model. So here I just call Crosswell score. Inside it I pass on the model. Inside the model already pipeline I had created, which will be doing the standard scalar, PCA, and SGT regressor here. Right? I had passed the input and the output data. And then here it is just giving you the results here, mean and the standard deviation. So in this way, we can use the SGT regressor. So just like we are having like other models in a similar way, like we are having other models in a similar way, we can use a SGT regressor also. We can use a SGT classifier also, so stochastic gradient descent classifier. So here we are having from sklearn.linear model SGT classifier. We can load any data set. We are taking out the input data here. We are taking out the output data. I'm going to call the SGT classifier here. Okay. Right. Crosswell score. Right. Crosswell score here I'm just passing model, input and output. And here mean and the results are given here. So just like any other model we are working with the SGT regressor or SGT classifier. Okay. Wait it now. Okay, just a moment. Let me open one file. Just wait, please. Give me 1 minute only. Your screen share is no more. Just wait, student. Just wait, please. I need to find one file actually. Just wait, student. Wait here. Okay. Okay. Fine. So just a moment, wait. Okay. Let's understand what is the Gini now, Gini and entropy. So, okay, now see here. See. Suppose this is the data set. In my data set, my Y output, I'm talking about the Y output now. My Y output is having the values 0, 0, 0, 0, 0, 0, 0, 0. Means my entire Y is having a 0. 0, what does mean? Only one type I'm having. So I will say my Y is pure. My Y is pure. I'm taking another Y now, where my entire Y has 1, 1, 1, 1, 1, 1, 1. I'll say my Y output is pure. So there is no use of ML. If I give this 1, 1, 1 on only 0, mean only one type I am giving. So my ML will not learn, my model will never learn anything because I'm giving a pure data set. I'm giving a pure values. There's no use here. So basically, I need impure. So whenever I'm terming pure, it means homogeneous. If my data set is having only 0, 0, 0, 0, 0, only that's all, I will say my data is having homogeneous values. My data set is having pure values, homogeneous. Here also I'm having homogeneous values. My data sets are having pure values. Okay, got the point? Homogeneous value. But if I say my data set is well when I am having impure data set. Impure data set. Impure means my data set has the values mix. Means my data set has the values mix just like 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. So here I will say my data set has a value of heterogeneous values, impure values. My data set is impure. I need the impurity in my data set. My data set is heterogeneous. So I will say this is a nice data set. My model will learn something. So the point is that we call this impurity. This impurity, we need the impurity. The impurity is known with the term entropy. I need the impurity. I need the entropy. If in my data set everything is 0, 0, 0, 0, 0, my entropy will 0. If in my data set my y output is 1, 1, 1, 1, 1, 1, 1, 1 only, so my entropy is 0. My entropy is 0. Okay. If my I say I have some mix of data, suppose I say some are 0, rest are 1, 1, 1, 1, 1, 1, 1 in this way. So I will say some percentage entropy I'm having. Or I'm having some, I say 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, some 0. So there is also some rate of entropy is present. But here, if my data set is having equal number of the provided categories, like 4, 0 and 4, 1 are there. So I will say my entropy is 1. So entropy means mixture of data, impurity of data. The more the impurity present inside the data set, more the entropy is. The more the impurity in my data set is present, the more the entropy is. High entropy gives good result. Now, this is a term entropy. Now, when we talk about the decision tree classifier, in decision tree classifier, we have root node, and we have branch node. Branch node. Branch node. So we are having a data set, column 1, column 2, column 3, column 4. So we are having a data set. Inside the data set, we are having columns. So which column will come in root node? Which column will come in branch node or sub-branch node? This all depends on the information gain. Information gain provided by every individual column. This information gain is achieved by various entropy levels provided by individual columns. Again, mathematical formulas are working. So in decision tree classifier, we do have two techniques to find out the entropy. One is Gini, another is entropy, direct. To find out the information gain, we do have two techniques inside decision tree classifier. One is Gini and one is entropy. Okay, so when we work with decision tree classifier, we do have two values inside decision tree, Gini and entropy, which shows various impurity level, that how much is the impurity present inside the data set columns and how much information gain we are having with the help of this entropy. So basically, entropy says entropy is 0 here, entropy is 1 here. Entropy is 0 here when all of the values are 0 here. Entropy is 1 here when all of the values are 0 and equalize value here. Okay. So basically, yeah, let's study about the Gini and entropy. So here basically, what is entropy? So you can see here, what is entropy? Entropy is the measure of homogeneity of a sample in a node. So it provides that how much your data is having the homogeneity, how much the mixture is present in your data. Okay, if the sample is completely homogeneous, the entropy is totally 0. And if your sample is having entropy 1, it means equal number of mixtures of different values are present there, right? So here, when we talk about the entropy, this is the formula working for the entropy. This is the formula working for the entropy here. Okay, so entropy measures the impurity of S. So it means S means data set impurity checking will be done with the help of entropy. And this one is the formula working for the entropy. So here you can see entropy is related to the machine learning. It is a measure of the randomness in the information being processed. It means how much information, how much randomness is present inside your data, how much randomness is there, how much impurity is present, how much impurity is present inside your data set. Okay, that is there. So if I say, suppose my data set is there, so inside the data set, if I say here that, just wait here, inside my data set here, entire data is same. So this is a 0 entropy. Here also entire data is same, this is a 0 entropy. And here, if I say, see, some of the mix of the data is there here. So some of the level of entropies are present here, like 0.66 or 0.5 or 0.4. So these are certain mix, some mix is present here. So some of the level of entropy is there. But if I say what is the 1 entropy? 1 entropy means equal mix of the data, means 1, 1, 1, 0, 0, 0. Means equal balanced data are there. So that gives you 1 entropy. So basically, here, when we talk about the decision tree, there are two values into the criterion, Gini and entropy. Okay, by default it is Gini. There is one more entropy here. Now here, decision tree classifier has to take the decision whether to go out or not here. So how it is going to take the decision? Okay, so here comes entropy or Gini. So here let's see. This one is the impurity criterion. One is Gini index, another is entropy here. These are the provided formulas. You can see it here. These are the again maths is present here. Gini index and entropy. So here I'll be showing you the data set and let's see how the values are calculated. You can see here some values present here. See here. This one is a conceptual learning. We are doing it here, right? Just to see it how the values are calculated. So here you can see 14 days data are there. Outlook, temperature, humidity, and wind 4 columns are there. Play tennis is given as the last column, which is a Y, which is a output here, which here it is showing whether the player should go out to play or not in the provided situations. Got the point here? Okay. Just wait here, please. Yeah, Sandra, PCA I taught last week. At the end, I taught last week. PCA, yeah. Okay, yeah. Okay. Now see here. Fine. Just wait here. Fine. So 14 days data are there. Play tennis values are there. Just wait. So here, if I say this data I'm taking, play tennis, this one's a Y data. So here, 1, 2, 3, 4, 5. So 14 days are there. Yes happened, 9 by 14, no happened, 5 by 14 here. It means 9 times, 9 out of 14 times, the player has gone out to play into different conditions in 14 days. 5 times the player has not gone out to play. So with this data, if one wants to calculate that what is the entropy of last column, of Y column, play tennis column, you can see here now. Play tennis column is the last column, which is having the values of play. Yes and no. This one I am talking about. So here, if one wants to calculate what is the entropy level, if we are having a 9 by 14 and 5 by 14 values here, I'll tell you, just wait here. Just wait. Just wait. See here. This one is a basic formula working for entropy. Calculate entropy of the target. This one is a formula working. Okay, this one is a formula working. So minus P plus means this is a positive. This one is a positive and this one is a negative. Okay, so here it is taking, like this one's a positive values now. So here it is taking 9 by 14, then log of P plus here. So 1 minus 9 by 14 minus, then this one is a P minus, this one's a minus means negative, no. So here 5 by 14 and here 1 minus 5 by 14. This one is a log P minus. So here, when it is calculated, these are there, these terms are there, entire calculations are shown. It is showing you 0.94. This is a 0.94. So this is the entropy. 0.94 is the entropy. What does it mean? It is showing that 94% is the entropy present inside the output. 94% is the entropy present in the output. What does it mean? Means here, if I say 0, 1. So nearby here, 0.94. So nearby here your entropy is there, 94. It is not 1. 1 will be reached when you are having 7 by 14 and 7 by 14. In that case, you will be reaching 7 by 14, 7 by 14. You're getting my idea? So here it is saying your play tennis target has 94% entropy. Now let's see what is the impact coming for this one. Now just wait here. Okay. Now I'm taking two more attributes. Suppose here humidity and wind. Let's go above. Here. Humidity and wind it is taking. Okay. Here it is taking humidity. High and normal humidity. High, normal humidity. Now one has to check it out how many high and how many normal. 1, 2, 3, 4, 5, 6, 7. 7 by 14 high. So remaining are 7 by 14 normal. Because total are 14 now. Total of 14. So in this way it will work. Okay, then just wait here. We need to think it. In high, how many times person has gone yes, person has gone no. So in high now, one has to check how many times no and how many times yes. How many times no and how many times yes in high, and how many times no and high in normal. One needs to check it out. So you can just count that. I'm coming here. Here. I'm taking this data. So okay, it is saying by this data I'm concluding 3 plus 4 minus 3 by 7 times the person has gone out to play. Yes. See here 4 minus 4 by 7 the person had not gone out to play. In normal case 7 times it happened. 6 times the person has gone out to play. 1 time the person has not gone out to play. Okay, now one has to find the entropy for high. Entropy for high. So one is to go according to the formula, okay, of entropy. So these values will be adjusted there, and the entropy calculated is 0.98. It means it is saying 98% entropy is there in high. In high case 98% entropy is there. So here 98% entropy is there. And in this case, 0.59 is the entropy after calculating. So here for high, 0.98, for here, 0.59 is their entropy. So what is the total entropy of humidity? Total. This one is the entropy, na? This 0.94 is the entropy for play tennis. One is to calculate the entire entropy. And then with the help of that, one is to calculate the information gain of humidity column. Okay, so here 0.94 is the total entropy of play tennis. 0.98 is the entropy of high. 0.59 is the entropy of normal. One is to find out the total information gain. Information gain for that one is taking the total entropy of play tennis target minus 7 by 14 into the calculated entropy, this one of high, minus 7 by 14. 7 by 14, you know what? This is a 7 by 14. This is a 7 by 14 value. So 7 by 14 into calculated entropy, 0.98, minus 7 by 14 into 0.59. Once this is calculated, 0.151 is the calculated information gain. of humidity column. So it means humidity column is giving 0.151 as the information gain. Now, similar way, one is to find out the entropy and the information gain for wind column. So here, if one wants to go with the wind column here, so one is to check it out wind column here. Okay. Wind column. So this one is the wind column, strong wind and weak wind here. So plate tennis, it is there. So strong and weak. It is there. So here it is saying, from here I'll tell you, strong and weak wind, total entropy is 0.94 of plate tennis. Weak wind happens 8 times, 8 by 14, and strong wind happens 6 by 14 times. Weak happen 8 by 14, 6 times happen strong winds here. Now we need that in weak wind, how many times the player has gone out to play or not. 6 times the player has gone out to play in weak wind, 2 times the player has not gone out to play in weak wind. In strong wind, 3 times the player has gone out to play, 3 times the player has not gone out. From this directly, 3 and 3. What does it mean? 3 and 3. 1, 2, 3, 1, 2, 3. So directly entropy is coming 1. So that's why your entropy is coming 1. Equal now. 3 by 6, 3 by 6. Now here the entropy is lower. That one is a 0.80, 0.81. So, okay, one is to find out the information gain. Information gain, it is taking 0.94, this one, minus 8 by 14, this total 8 by 14, multiplied by entropy, then minus 6 by 14, this entire 6 by 14, multiplied by 1.0 entropy. 0.048 is the 0.048 is the information gain. This is the information gain. Okay, so that is there. Okay, so that is there. Now, here, see. So it means here now, you need to see that humidity information gain is what? 0.151. Wind column is what? 0.048. Okay. Outlook is in a similar way, students, same thing will goes. So here, let me take out the data directly. Outlook is giving. Outlook is one of the column. Here, how much entropy? 0.247 is the entropy. Same calculations will go. So here, for temperature also, it is 0.029. So here you can see this one. Just wait now, see. What is the information gain total? You can see now. See this one. No. See the highest one. Students, see here. The highest one is going with the outlook. The highest information gain is going with the outlook now. This 0.247. So here, outlook, the column which gives the highest information gain, that is 0.247, that one is outlook. So that will become the root node. Then your humidity, that one is a 0.151. Then wind. Okay. So that is there. So in this way, your root node and branch nodes are created here. Just see in this way. This is calculating for the outlook. Here. So outlook is the root node, then humidity, and then wind. So means here the hierarchy which it is having for the given ascending order it is taking here. That how your decision trees are created internally with the provided information gain. This one is the entropy I'm talking about. Okay, this is one case here. Gini and entropy found in decision tree only. Yes, exactly. Here, Gini and entropy helps to find out the information gain. On that basis, your decision tree classifier tries to build up the root node and the branch node. Okay, and also it gives you the betterment of the results. The betterment of the results. If any column is giving the highest information gains, it will use the formula and find out your results also. Right? Okay, just wait. So they are into the decision tree only. Suppose here there is one more Gini. So here Gini index. So here you can see this one is a formula for the Gini index. 1 minus sigma p square j is equal to 1 to n, means the total number of rows we are having, it is taking p square j. So here just wait, I'll tell you how it is going to work with the Gini index here. This was the same example we are taking. So let's see the way here we worked with for the to find out the entropy, how the things changes into the Gini index, Gini. So here on the same data set here I'm taking. This was the Gini index, you can see, very easy. So here you can see, suppose here you are having a wind column. You are having a strong wind, true, and weak wind. So true is a strong wind, weak is a false wind here. Here in strong wind, 3 times the player has gone out to play and 3 times the player has not gone out to play. Okay, so it means total 6. So it means 3 by 6 and 3 by 6. So it means 3 by 6 times the player has not gone out. The player has gone out to play. 3 by 6 the player has not gone out to play. Here 6 and 2. So here 8. So basically 6 by 8 and 2 by 8 here. So here 6 times the player has gone out to play and 2 times the player has not gone out to play here. Okay. So here inside the wind, one is to calculate the Gini. So here it means this true wind means strong wind happens 6 times and 8 times weak winds happen. So 6 by 14 here happened and 8 by 14 here happened. Okay, that happened. Now one wants to calculate the Gini index. One needs to calculate the Gini for this. One needs to calculate the Gini for this. So basically one needs to calculate Gini for strong wind and then weak winds here. Okay, so that one is here 1 minus see here 1 minus 3 by 6 means this value, making the square of it minus 3 by 6, taking this value, means both of the value which are here. Okay, one can calculate the value. After calculating the value, it is giving the value of 0.5. Then one is calculating the value of 1 minus the value of this one, 6 being a 6 positive. So 6 by 8, making the square of it minus 2 by 8. This one. Got the point here? 0.5 and 3.37 here. Now here, this one is only 0.5 is calculated for this one. So 6.5 into 0.5 and 8.14 divided by 0.37. Okay, they both will be added. So here 6 by 14 into 0.5 plus 8 by 14 into 0.37. So 0.42. So it means Gini index for wind. What is the Gini index? 0.42. Same way, one is to calculate the Gini index for humidity. Same. One is to find out high humidity, normal humidity. Play tennis, that 3 times positive, 4 times negative, 3 times the player has gone out to play, 4 times the player has not gone out to play. So it means if I take the data from here, 3 and 4 here. So 7 times high humidity happened out of 14. 6 and 1, 7 times the lower humidity, normal humidity. 3 and 4. So 3 by 7, 4 by 7, 6 by 7, 1 by 7. The same formula will be used. Okay, one is to calculate the Gini index for individual, then for entire. What is the calculated Gini index? 0.36. So for humidity, 0.36 is the Gini index. The similar way, one is to calculate the entire Gini for different temperatures, you can say, different various temperatures, you can say it here. They could be calculated here for all the columns here. Okay, so what are the various values here? So you can see here, you are having here outlook, temperature, this one. So you can see in this case, you are having the highest one is a temperature basically. Highest Gini index is for 0.44 now. So temperature will be the root node. And then this windy, this is 0.42. Wind is there, and then your next humidity is there. And this impacts the your accuracies also. So it takes the data set, calculates its Gini or this entropies, and gives the accuracies also. So basically what happens now, see here, basically what happens in case of decision tree. When we work with the decision tree, okay, so there in decision tree, we give decision tree, just wait. In decision tree, we give the value criterion. The criterion could be either Gini or entropy. You can keep any. The criterion could be either Gini or entropy. Okay. So either we give a value of Gini, or by default Gini is their default. So when we work with the criterion Gini default, you can see your accuracy. If you are suppose your accuracy is 0.78, you want to improve, you can write criterion is equal to entropy and see whether you are improved. If you are reaching to 0.90 or above, you can stay with criterion entropy, or you can choose your criterion wherever you are at the highest one. So this all depends with the information gain here. It gives all the accuracies with the provided information gain. Okay, so in this way, your this tree classifiers work basically. Entire maths is there, everywhere maths is there. Your entire machine learning is based on entire mathematics. Okay then. So this is overall for Gene index here. Okay. Okay, then for today, from my side, this is overall. Rest tomorrow I'll continue. Tomorrow I'll do your unsupervised learning. That's all for today. Thank you. Thank you. Thank you. All the PPTs, all the documents, everything is present inside the elements. Everything. You need to find out the section. In the end section, you will be finding it out. Okay then, bye. You can find out everything is present inside the elements.